Good day, everyone. My name is Kumo, and I'm a course advisor located in our Johannesburg support offices in South Africa. Thank you all for joining us today for this presentation that will be hosted by Dr. Abate. So, if you could just maybe kick off the session by letting us know in the chat box as to where you are attending this webinar from, which part of the world you guys are from. And I'd like you guys to pay attention to the notifications. If you could just turn them off to minimize any disruptions that may occur while the presentation is happening. And secondly, I'd like to notify you that you can use our Q&A function. And the Q&A function, that's where you can put in all your questions, and then we can answer them either as we go or towards the end of the session. But Dr. Abate will be able to let you know how he would prefer that to happen. Okay, so for this presentation, there will be a certificate of attendance, and that will be sent to you within 4 business days. So please check your emails for that. If you don't find it in your email inbox, then you can check the junk mail or the spam, alternatively the promotions folder. So the copy of these slides, as well as the video recordings, will also be sent to you within 2 business days from today. So just to let you know a little bit about EIT and our offerings and what sets us apart is the fact that EIT is an engineering specialist that offers industry-orientated programs with our world-class Australia accredited education. So that's made possible by the industry experienced lecturers and our unique delivery model. And we have 2 other institutions, so to speak, 2 entities apart from EIT, one of which is ECST, which offers online UK qualifications. And currently we are offering 4 HE courses, 2 bachelors, one in industrial automation and the other one in electrical engineering. Whereas our master's programs, we offer power system analysis and renewable integration. And the other one that we do offer is the industrial automation and instrumentation control. So we have just recently opened our South African ECST, which is the Engineering College of Science and Technology. And that is a South African accredited qualification with on-campus offered as well. So it's basically a blended delivery model for the courses that we are currently offering. So you can go and check out both our entities when you get a chance. And lastly, I would just like to notify you that each of them have their own website. So if you are looking for a certain qualification, please make sure that you are looking in the correct website, okay? And in terms of the conduct for today's presentation, just follow my instructions and we can have a smooth sailing presentation. So today's webinar is performance-based design in practice, a step-by-step guide using a 4+G RC dual system structure, and it will be presented by Dr. Abate, which he is a structural engineer as well as EIT's lecturer. So, Dr. Abate, if you'd like to take control, please do so, and you can go ahead and start with your presentation.
Okay, thank you, Kumano. Thank you. Welcome, everyone. So today we are going to have a presentation, performance-based design in practice. a step-by-step guide. And this presentation will be very useful for beginners and even structural engineers who have never done performance-based before. So what we are going to do, I will share my screen. Can I share my screen?
Yes, sure. You can take control.
Okay.
So, if you could just check on the options to take control.
Yeah, the entire screen.
Are you managing?
Yes.
There we go.
Okay, great. Okay, so what we are going to do, this is the presentation. Can you see?
Yes, sir. Perfectly. Thank you.
Great. Okay, so what we are going to do, performance-based design in practice, and we will go here and to the software also. We have ETABS software for linear analysis, and we have also another for nonlinear analysis. And so perfect. So today's agenda will be structural modeling for PBD, including material property section definitions and load pattern and performance objectives based on FEMA 356 and ASCE. And we will use also ASCE 4117 guideline. Then we will see also pushover analysis, evaluating structural performance and overview of performance-based design. And if I can, I will show you also performance-based, how to transfer from ETABS and SAP to perform 3D for assessment, and focusing on structural behavior and nonlinear analysis techniques and so on. So in general, don't worry, we are going to talk, as you can see, we are going to talk a lot today. The first one, module 1, we are going to discuss why we need PBD and why code base is not insufficient in performance levels like immediate occupancy, life safety, and collapse prevention. Then earthquake hazard like service level, DB, and MC level. Then we are going to see also the modeling part, okay? Modeling part for linear analysis, for initial code-based design, and from ETABS and SAP, how to transfer to performance-based design, and material definition, section, diaphragm, and load cases, okay? Then from linear analysis, we are going to jump into nonlinear analysis. Then we will see the difference between plastic hinge modeling and fiber modeling. Then pushover analysis, nonlinear times tree analysis, performance point, and this acceptance criteria as per ASCE 4117 as well, okay? Then the case study for this presentation will be G+4, and we will see also the geometry, material, and load, and linear versus linear result as we have seen now. And we will see also DC ratio and hinges. Then we will see performance evaluation, okay? And we will say a little bit about also ASCE 31 31819. This is the Appendix A. This is the new for performance-based, which is added in the code for MCE level, okay? Then we will see also we have published some research papers. So we will show you that as well. So in general, this is what we are going to do, and the load cases and model transfer, okay? And performance evaluation. And there is a very useful tool in Perform 3D. If I can, I will show you, but I will show you, and demand capacity also, and result combination and envelopes. Then performance weight determination also. I will show you in the picture how to demand and capacity in the pushover. We will see that. Okay, so for your information, at AIT, we published a lot of peer-reviewed journals, and these are the published. You can read very well. It will give you a tremendous amount of information about performance-based design. and especially this global research trend in performance-based structural design and comparative bibliometric analysis. This paper will tell you a lot of information about performance-based design, why, and in the world also, which university are publishing a lot, which country. And this is a bibliometric analysis, so you can use that. And as you know, this is the third part of our webinar, and you are invited to go and check part 1 and part 2 of performance-based design as well, because we show them detail how to design from scratch linear analysis, okay? So today it's a little bit, so we go deep in the technical part of performance-based analysis. And this is the team in our EIT. And for the guidelines, you can use like ATC, FEMA, okay? All these guidelines, ASCE, TBIs, and ASCE 4117 also very important. So these are the guidelines which you can use. And about the software, you can use SAP, ETABS, Perform 3D, CSI colon, very easy softwares, and you can find them here, and you can use. The other thing for linear time tree analysis and non-linear time tree analysis, we use Sesimomatch. This is also a free software. If you have organizational email, you can register and they can give you. You can use it for matching, okay? Matching and scaling of earthquake. We will see it later. And Extract also very nice software, and ETABS also. So this is our webinar. This is the project description. Today, what we are going to see, G+4 building. This is just a sample building, and this is a perspective, and this is the floor plan. And as you can see, G+4, and the concrete grade will be C25, and the steel grade will be S450. And for you can optimize, but for now, beam sizes like ground floor 60 to 50, 60 to 50, all. And for the floor also, we use 60, and roof floor 60, 600 by 250 mm. Column size will be 600 mm by 600. The slab thickness and wall thickness. This will be for initial purpose, and we shall see them. Okay. And these results are from Perform 3D. After you transfer your model from linear analysis, then you have in Perform 3D also we will discuss. We have modeling part and analysis part, and this is also for this is for run, and this is for modal shape and so on. This is for advanced. Once you finish in ETABS, you can transfer the file to Perform 3D, and you can make a lot of analysis. You know, this is for hysteresis loop, and this is pushover, and this is DC ratio and the envelope, and these are all taken from Perform 3D result for our G+4 building. These are some of the results. We will see it in the moment. And this is moment shear, this is the stress distributions and displacement. And this one is the how to change from linear elastic analysis to non-linear elastic analysis. We use plastic hinge modeling for beam and column, and for shear roll, we use fiber hinge modeling. And these are some of the immediate occupancy, life safety, and collapse prevention sites. So now we are going to start from part 1, which is code-based design basics. So as I told you, this is the paper which is published at EIT. And the literature review, we use voice viewer, and we examined around 3,469 papers related, PVD related papers. And these papers span from 1983 until 2024. And we use voice viewer. And from this, we try to see the preferred journals, leading countries, leading organizations, international institutions identified using Scopus database. And as you can see from here, starting from 1981 until 2023, the awareness of PVD rising, you know, throughout the country. And because of the difficulty, performing PVD is not a must, it is it's your option, and the client, if he needs to do performance based after you do code based, you can do it, but it is not a must PVD. So these are some of the things. For example, from there, what we see, for example, previous studies have lacked crucial components such as local soil condition, ground response analysis, topographic influence, active fault characteristics, split groundwater behavior, and slope considerations. If you just adopt code, for example, Eurocode for your country without examining your geological aspect of your location, it will be very difficult, because if you have, for example, earthquake, very small earthquake from the epicenter, for example, here, and if this is the strata is rock, okay, if this is rock, and while the earthquake is like, let's say, 100 kilometers from the epicenter, let's say your area is soft soil, okay? You know what happened? At this point, the earthquake will be magnified like 3 times or 4 times. That means the earthquake which starts from here, because of soft soil problem, it will magnify. So you know how much your structure will be different. So simply adopting European code or ACI code is not the solution. Okay, so every local, these things, crucial component like local soil condition, ground response analysis, topography influence, actual fault characteristics, slip rates, all these things should be studied. So as you can see from our study, we see from visualize co-occurrence, all key analysis result, we see performance-based design is the more studied word, and United States was the biggest contribution in the PVD. Again, here in the countries and engineering structure, this is a journal which publish a lot about PVD. And as you can see from here also, if you make linear analysis, and this will be the result you get. If you make non-linear analysis, you get, this is the result. So you get completely different result from linear analysis and non-linear analysis. So if you make linear analysis, most of the time, as you can see, the result is wrong. That's why we are using CD factor for amplification of displacement. So this small area, this is the area which can simply told you why performance-based is required. And from our literature review, we see that code-based design cannot address earthquake issues, and PBD is cutting-edge seismic design technique. And the effect of using prescribed adopted code without amendment, as we have seen, it's very wrong. So in general, from overall, this study provides comprehensive overview of the research on performance-based design and identified the key research topics and future directions. So the hypothesis we made was the characteristics, the challenge of adopting seismic design code without necessary adjustment, accompanied by the absence of reliable seismic map in the country without earthquake recording stations, may lead to structural failure, as we have seen now, the magnification of earthquake. If you have small, then because of soft soil, it's magnified like 3 or 4 times. So if we use performance-based design, maybe that is the solution for countries which doesn't have code instead of adopting. That's what we said. So let's see with general concept. The general concept is the common structural systems, as you know, we have force, lateral force, like earthquake, wind and earthquakes, and we have displacement, and we have base shear, as you know. So we have gravity loads, and we have also diaphragms, moment resisting frames, and gravity frames and foundations. So from the system, gravity load resisting systems could be vertical or horizontal. We have slabs and beam and column, let's see. And from lateral load resisting systems, we have vertical element and horizontal element. So for example, this vertical element, we have shear roll, column, bracings, as you know, and horizontal diaphragm, slab diaphragm. So type of structural systems, for example, we have bearing wall. This will be the gravity and lateral loads will be resisted by 100% resisted by bearing wall. And for this one, gravity frames, the frame is responsible, yeah, for to resist the earthquakes, okay, gravity frames. For moment resisting frames, both the gravity and this 100% will be resisted by the frame. And dual system, some of around 25% of the system will be resisted by column, okay, this frame, and the remaining will be resisted by shear wall. So this one, what I mean by this, this is our linear analysis. So let's say we want to see the shear force, maybe. Okay. You can use, okay, apply. So we want to see the shear force. If this is the shear force, for example, let's see what we can do. I think we have the draw sections. If you draw the section here, for example, as you can see, the force like 11,263 is resisted by column, floor, beam, wall, bracing, and links. Yeah. So if you just remove this and to see how much of the force is resisted by the column, now we don't have any shear wall, okay? Because we don't have any shear wall, full force is resisted by the column, okay? But let's go back to here. So in this case, this one, if it is dual system, at least the column should take care 25% of the force, okay? Even if you add shear wall, sometimes you think you are using dual system, but if the force is not resisted, 25% of force is not resisted by the vertical system, it is not dual system. So you have to check as we have seen now. The other general concept, you know, we have base shear and displacement as we have. And if you design, for example, if you design with against linear forces, your section will be very big, you know. But if you divide your linear forces with response spectrum, as you can see, and we have overstrength factors and we have R factors, all factors, this or omega, overstrength factors, all these things, then you're gonna have nonlinear forces. In nonlinear forces, you can design with a small section, but a small section means it should be ductile enough, you know. You have to make it ductile. If you cannot make it ductile, it will be very difficult. It will not resist the earthquake. So you have to make it ductile enough to resist. Making a small section means it doesn't mean economically. I mean, sometimes you have big section, but when you use nonlinear forces with small decreased by R and this, you have to take care the ductile detailings. That is one thing we want to tell you. The other thing, the evaluation of building design. And sometimes, you know, as per this, Los Angeles tall buildings, they say to say a building is tall, at least it should be 48 meters, 16 story, okay? And the evolution of building design, as you can see, we have masonry and we have moment, then we have tube system, then breast, and then concrete coils and the concrete core with outriggers, okay? So depending on the earthquake and the complexity of your building, you can choose which one. And we have also different type of structure. As you can see, we have bracings, okay, outrigger columns. As you can see also here, we have coral and outriggers. And we have also here regular, irregular shapes. And we have also a precast and RC buildings, okay? So the combination. So as a structural engineer, you are allowed to choose which structure you want to. Then the most important question is my structure safe? As structural engineer, you have to ask this question. And we have ETABS, SAP, perform, and nonlinear time history analysis, pushover, and other analysis types. And you have to make sure the performance point. So performance-based seismic design of tall building, key point of performance point, this PBD code provide a minimal level of safety for a building type, yes? And many code requirements are not tailored for tall buildings as well. So performance-based seismic design is a framework for designing new building. It is a framework, by the way. It is not a code or something, okay? It's a framework, and it will give you alternative design with predictable and safe performance under earthquake conditions, and required more effort. As you can see, PBD is not like code-based. It needs more effort and analysis and design. The other thing for developers and structural engineers, make exceptions to specific for the limits, okay, code limits for seismic force resisting systems, for example, and utilize advanced seismic system, not in the code like outriggers, as we have seen, and use high strength materials, devices, base isolations, and turn this mass dampers. So it gives for structural engineers, developers and structural engineers a lot of option. Then when we come to building industry, dependence on code and standards, as you can see, key role of the building codes. The first thing, they will establish requirements, yeah, and provide the standard solution and outline detailed procedures and draw from experience and ensures the code guide and define estimated hazard load levels and prescribed limits on the structure member and so on. Yeah, this is the use of code based. And as you know, we have disaster, and disaster is hazard times vulnerability and exposure, and hazard times vulnerability will be risk, yes? So to reduce risk of disaster and increase safety, what we need to accurately assess the hazard and mitigate vulnerability. Then in this way, we can reduce. The other thing, the prescriptive code, protection and practical limitations. For example, public perspective, owner perspective, and engineer's perspective. So the public always, they ask, will this building protect occupant during an earthquake? This is their concern, yes? Is collapse prevention adequately addressed? This is what they are asking. The owner also will ask, will the structure remain standing after strong shaking? This is what they are asking. Can the building be occupied immediately after earthquake? How severe will the damage will be? And all these things, okay, how long will recovery takes? This will be the concern of the owner. And what will be the engineer answer? The structure satisfies code requirement, but post earthquake performance is uncertain. This is what the structural engineer will say, because the structural engineer will follow the guide like prescriptive code. He will follow the code, what the code says. After that, because why I'm saying this, mostly when the earthquake comes, most of the time the building fail, even if they follow code-based design, yes? So the structural engineer will not be responsible. That's what at the code-based, this will be the structural engineer answer. Then always we have to follow DC ratio. If the demand is less than the capacity, then we are safe. And if the demand is greater than the capacity, unsafe. This is even for the strengths, we have reduction factors, safety factors included. But prescriptive code are primarily intended to prevent collapse and protect lives, not to ensure minimal damage, immediate occupancy, and rapid recovery. This is the idea of code. But even if we are saying DC ratio, there is a lot of uncertainties in the demand side and in the capacity side. For example, in the demand side, we have load type, okay? and statistical averaging, and definition of load case, structural analysis, and combination of loads and envelopes. In the material sides, we have tests and we assume some values, and we have section sizes and based on failure criteria and reduced by safety factors, all these things. So both demand and capacity are based on multiple assumptions, okay? Simplifications and statistical estimations. Therefore, the DC ratio is not an exact measure of true safety, but an indicator within a code-based framework. So this is very important. In the code-based, in the demand side and in the capacity side, we have a lot of assumptions. So we cannot rely on code-based. So before we go to performance-based, let's go to the linear analysis and let's say something. Okay, so this is our linear analysis. So what we are going to do, the first thing we are going to do for performance-based analysis is you have to model linear analysis. In the modeling, you have to come and you have to have material, as you can see, concrete and all these things. Okay, weight per unit. You have to, once you choose the code, it will give you. Okay, it will populate. The ETABS is very helpful when you choose. It will give you, but you have to also correct. For example, weight per unit volume 25, something like that, mass per unit volume and modulus of elasticity. And these things, as per the concrete, you can go and Poisson ratio, for example, Poisson ratio 0.24 crack sections. Yeah, if you make it 0, it will be uncracked sections and so on. And for steel also the same. Okay, for steel also, this is for tendon. And this is for, as you can see here, this is rebar. So we have also defined the rebar. The first thing is from definition. Then from here, section definition. In the section definition also, you have to define beam section and column section. Yes. So for example, beam. The most important thing in the cross-section definition is modifiers. As you can see, for modifiers, we give 0.5, 0.5, and torsional constant 0.1, and moment inertia 0.5, 0.5. And this is very important. If you don't make, okay, 0.5, it will be very rigid and it cannot transfer load from beam to column. That is a problem. And even we can see one example later. Because if, for example, if you, in the section definition, a slab, for example, we have this slab, and in the modifier, you see modifier for membrane action and bending action, because we don't have shear action. Yes, shear action will be for thick slabs, but in the thin plate, we have membrane action and bending action. So for these two actions, you can give 0.2. If you don't give 0.2, what you will get is, let's go to ground floor, for example. And if we see moment, let's say moment, and sorry, bed. Okay. Okay. Let's see also the value. For example, if we see here 12, 12, 10, 10, this is the moment transfer from slab to beam, yeah? But if you make the slab, for example, if you don't give modifier 0.5, 0.5, if you make it 1, 1, 1, 1, the moment will not transfer into the beam, okay? And you will get very small moments, very small moment. That means you will not get the required amount of reinforcement, okay? It will not transfer the load from the slab to the beam and from the beam to the column. So all the sections, even the column, if you, the column, if you go to the column here, and modifiers, as you can see here, 0.5, 0.5, okay, and the original 0. If you don't give this one, you will not get the exact amount. So what I told you now, in the material definition, you have to take care whether it is cracked section or not. And in the section definitions, you have to take care that you give modifiers in the slab. And the other thing, what you have to do in the preference, if you come here in the preference, you can choose the Eurocode. As you can see, we are using Eurocode. And the load combination also, we have two, as you know, we have two load combinations, 6 to 1. And all these things you can go and see, okay? Very important. When you do like this, it will give you, for example, the BC ratio. This one is for the column. Column should be designed to make sure that the beam column capacity ratio remain within the limit, yeah? That means the moment, the beam moment should be 30% less than the column, yeah? Because the beam should fail before the column. If the column collapse, the global collapse, okay, all will collapse. So, but if beam collapse, it will be local collapse. So this should be, you have to take care. The other very important thing, as you can see here, theta. This will be for the imperfection, okay? For the imperfection case, we use here. So even if you don't define load case for a notional load case in your load case, if you make 0.5 here, already the notional load case is assumed for the imperfection case. The other thing is gamma steel and gamma concrete. You know that 1.15, 1.15, and alpha CC for compression and tension. If your location for concrete is very good at the quality, you can make it. Otherwise, 0.85, 0.85, you can do that. And the other thing, this is for post tensioning. This is for top fiber and bottom fiber. So you have to take care of these things, okay? The other thing, what we do, the diaphragm also, we have diaphragm. Let me make it like that. And here, and here. But in our second video, we gave you step by step how to design, okay? This one is only for your information, okay? What I want to show you now, hinge and can you see here? Sorry, this one, diaphragm extent. I want to show you here. This is the diaphragm. This is the center of mass, okay? This is the center of mass. And for center of rigidity, you have to go here and if you click here, calculate diaphragm center of rigidity, then after calculation, the software will give you the difference between center of mass and center of rigidity. This one, as much as possible, the center of mass and the center of rigidity, the distance should be lower. Otherwise, you're gonna face torsional irregularity, okay? So that is the problem. So as much as possible, the rigidity, the center of rigidity and center of mass distance should be lower. Otherwise, if you go to the here, let's try. Maybe it will take time, but for example, in the mode shape, what you are expected is that mode 1 should be translational in the X. Okay, this is, as you can see, translational. And mode 2 should be again in the Y, translational. And mode 3 should be torsional. You see? So this will be torsional. Maybe let's start. Sorry for this. Depending on the specification of the model. Okay. Anyways, so this is what I want to show you, okay? And the other thing in the definition, all these things and the mass source. Some of the problem in the mass source, some people, you know, they take element self mass and additional mass. Again, specified load pattern. And if you take these three, and if you add load, the dead load and the element self mass will be added together, okay? And that will be a problem. So you have to take care. If you check specified load pattern, so you don't have to check elements. And we don't need vertical masses because we need lumped mass. This is lumped vertical mass and the included lateral mass. And this one for live load, we need psi2. There is a coefficient from the code. That's what you have to use here. And the other thing, load pattern. This is the load pattern we have. And in the load cases, for this demonstration, we use almost all equivalent lateral force procedure, response spectrum, as you can see. And we use ELF, equivalent lateral force procedure. And after that, we use linear time history analysis. This is linear time history analysis in both direction, and we mashed it, okay? And how to bring, let me, if we have the, for example, okay, this is peer ground motion. You go to peer ground motion database, and the peer ground motion database, you can download different earthquake data. Okay, these earthquake data, okay, will give you. Okay, these earthquake data will give you. I will show you here. For example, this one, modify. Here, define function and time history analysis. Oh, sorry, because it's not reading. For example, this one, modify show, because the data now I took is, this is how you define. Okay, when you match, you can come here, and the most important thing is when you match the from 0.5 T fundamental period to 2T, the matched data should not be less than the target response spectrum. Okay, because here what you can do, define response spectrum. This is target response spectrum. So once this, for our case, we use this target response spectrum because this is the site response spectrum. So you have to match it with this response spectrum. Okay, so that is another concept, because matching for performance based, it is very important. Okay, for performance based, first you have to bring the data, okay, from file, and it will now it is already locked. It will not take us. You have to bring the data, the earthquake data. Once you bring the earthquake data like X and Y directions, and you have to match it, match to response spectrum, and you have to match it. When you match it in the when you match it, you will match it in the frequency domain and the time domain. Okay. Then whatever will give you, for example, matched one, you can, okay, use this one. Okay. What we want to see, I think it's not responding also. Okay. This is the linear analysis. In the linear analysis, you have to do all these things, and you have to design your structure, and you have to get the section and the reinforcement, everything it should pass. Okay, I don't know, it's not responding until it's responding. Let's go back and let's continue our discussion. Okay, let's say now we are okay with linear analysis. Then what we are going to do, we are going to change the building to nonlinear analysis. This is our nonlinear model. Nonlinear modeling, you can do it in both ways. For example, that linear analysis is changed into nonlinear now. This is plastic hinge modeling for beam and column. Okay, And for frame, for example, let's show generated. These are the plastic hinge models that are generated. This is for column, and this is for the beam, okay? And for example, if we see, sorry, okay. As you can see here, for the column, for that particular hinge, we have immediate occupancy, life safety, and collapse prevention. This is the capacities, okay? ETABS directly give you these capacities. So what we are going to do, let's go to here and we will come back there, okay? And I hope this one. Okay, we will come back here in a minute. Let's open that linear, the linear one. Sorry. It's crashed. Okay. So let's open. Okay, we have sample, yeah. So no. Let me open this one. It's opening. Okay. So this is the. So what we are going to do, the analysis is already done. We check, and let's say we want to design. Okay, we check the preference, everything, and let's say we see everything. So let's design now. Now the program is designing. So as you can see here, the design is over. So you will get, this is the reinforcement you will get, okay? This is the reinforcement you will get. And let's say we want to see the beam, and let's see the detail, for example. As you can see, this is the beam. Everything what you give, the section, everything, the elastic modular, FCK values, ASA, FYK, all these things, diameter, as you can see, alpha C, alpha CC, all these things. And this is for lightweight, and for shear force and reinforcement also. We have ED, VRD, VRDS, all these things are given, okay? So, for example, here area of steel is given already, okay? Area of steel is given because the concrete capacity is 43, which is the demand is 44, yeah? So if the shear carrying capacity of the concrete is less, then we will provide steel reinforcement. And you will go here, and the other thing, for example, you have to go here and display design information, and you have to see all this rebar percentage, shear reinforcement, column PMPM interaction, and beam column capacity ratio, column beam capacity ratio, joint shear capacity ratio, torsion, shear torsion, and general reinforcement, and all. If you don't want, you have identify all failures. So if you go for here, and if you say identify all failures, maybe some areas you might get some kind of failure. So take care, okay? Maybe this kind of failure also, even if the reinforcement, everything is passed, maybe you will see some kind of failure. So once you are satisfied, this one, as you can see here, you go here, export, and here you see performance based, perform 3D text file or perform 3D structural file. If you want, you're gonna transfer this file into perform 3D. But for performance based, this is the initial point. You have to know the reinforcement. Okay, you have to know the reinforcement. So display, and for example, longitudinal reinforcement. Now you should know this amount of reinforcement. After that, we will go to nonlinear. Okay, we will change the model, and I will show you how performance based will be used. So let's go to now our presentation, and we will come back later. So this is performance based basics. So as you can see, we have linear analysis and nonlinear analysis, and we have equivalent lateral force procedure, response spectrum, linear times 3, and nonlinear, this linear times 3 analysis. This is direct integration. This is using the concept of mode shape. And when you come to nonlinear, we have pushover, nonlinear modal response tree analysis, and nonlinear times tree analysis, which is also the same. This is fast nonlinear analysis. Linear analysis procedure, material stiffness property remain constant, no yielding, damage, or other things. And when you come to nonlinear analysis, we have cracking, yielding, damage, and expected this modeled nonlinear stiffness varies. So linear analysis assume constant stiffness and pure elastic behavior, while nonlinear analysis capture actual inelastic response, damage, and stiffness degradations. Therefore, nonlinear analysis provide a more reliable measure of structural performance. And these are some of the questions we ask for our research. For example, does the absence of earthquake recording station and reliable seismic data pose a significant challenge for a country without the means to generate accurate seismic? Some countries, they don't have hazard also. If cannot trust our current seismic hazard map, then we have to use performance-based will be a solution. And after that, all of the solution, linear and nonlinear results will be checked. Okay, will be checked. So this is the idea. As we have discussed, we have MC level, we have DB level, and we have design level. So from the MC level to design level, we have 2/3. From DB level, we have R factor, as we have discussed, and overstrength factor. Okay, and the R factor and omega factor will vary from this range. So all this gray area will be in the linear analysis. This will be a guess. Okay, but the idea of performance-based design is instead of guessing and using this gray area, why don't you know the exact force deformation capacity and stress strain curve of the material for concrete and for steel? And once you know the capacity, just use MC level and know the performance at MC level and service level for serviceability. This is for ultimate limit state, and check the performance. And without any guess, you can know the performance of your building. That is what the performance based in this simple structure showing. So from the design, as you know, we had intuitive design and code-based design, performance-based design, and consequence and risk information, resilience. So this is the criteria we are going. This is what I told you now. If you have steel, you have the stress strain curve, and for concrete, and you have to put this into your structure. And we have the moment curvature and moment rotation you apply in your building. And once the building, when the earthquake comes, then it will show you the immediate occupancy, life safety, and collapse prevention. Okay, this is the hinge. Okay, this is the hinge. So this is the performance-based, use real material property and expected values. Not only that, because the expected value for steel is 1.17 and for concrete is 1.3. So at least we will increase the expected value. So expected strengths for concrete and rebar, and reinforcement detailing also. longitudinal and shear must be defined before nonlinear analysis. That means required initial linear code-based design. This is what we have seen now. In the linear analysis, you have to design and you have to get the initial rebar from linear analysis, provide cross-section geometry and rebar layout. This is the initial. Then transitioning to nonlinear modeling, convert the model to nonlinear as we have seen now. I will show you. Then assign appropriate hinges, like for the beam, column, and shear. Okay, plastic hinge modeling and fiber hinge modeling and so on. Then define moment curvature and moment rotation. So we use moment rotation and section property and material strength behavior. Why we use nonlinear modeling? Capture both local member level and global structural behavior, represent the structure as close to reality as possible, and enable realistic simulation of moment, shear force, and drift displacement, and so on. And design and evaluation capacity, PBD is capable to both new building and assess existing building, allow for site-specific hazard input or nonlinear pushover in time history analysis. They are used. So this is the same thing, performance-based workflow. First, you have to do linear analysis, but you have to start from architectural design, and you have linear elastic model and determination of true capacity. So for linear elastic, you can use ELF or response spectrum analysis will do the job for you. After you do that, we go to advanced nonlinear. Okay, this will be SLE level, service level, and MC level analysis, and performance assessment with SLE level and MC level. Then check the acceptance criteria. If it is okay, success, complete design. If it is not insufficient, then you have to go back to linear and you have to change the section. Okay. So by doing so, you can check all these model results, base shear, story drifts, all these shear, strengths, DC capacities, all these things can be found. This is the overall idea. So we have operational, immediate occupancy, life safety, collapse prevention from 0 to 100% as FEMA 451. This will be your building capacities as per your force deformation curve, okay, moment rotation curve. So this is the same thing. And for your criteria, key structural performance indicators, you have stiffness, stability, strength, deformation, drift, ductility, damage, damping, energy dissipation, and acceleration. All these things will be agreed in the board, PVD board, okay? When you have, because this is performance-based design, you have to accept how to perform. What percentage of, for example, immediate occupancy could be? For example, life safety, maybe 70% of collapse prevention or 60. These kind of things will be agreed with the performance board. And this is the PVD methodology we used in our EIT for 44 story and 100 story. We perform performance-based design, and we try to analyze all linear and non-linear analysis. As you can see, classical model analysis, repose spectrum analysis, linear time dynamic time analysis, and pushover in linear time industry analysis was performed. And this is what we have discussed now. And the other thing, this is the earthquake we used from peer ground motion. We extract this imperial vary, lenders, memos, and all this earthquake was extracted from the peer website. And the idea is for linear or non-linear analysis, both the procedure is the same. You have target response spectrum, okay? And once you have target response spectrum and all, you have to scale it. For example, before scaling, the earthquakes may be like this. All the 11 earthquakes may be going like this, okay? But after that, you have to bring it down to your response spectrum by matching and scaling, and from 0.5 T fundamental period to 2 T fundamental period, these values should not go down from the response spectrum. Then the result, whatever you get, will be, for example, this is 11, yeah? So you are going to get 11 results, 11 moment, 11 shear, 11 drift, 11, all this, we will see it later. all these things. Then you have to average it, okay? M1 plus M2, M3, and something like that. This is the matching what I was talking about. You have frequency domain and time domain. Sometimes time domain will give you good, and but it will take time too much. And frequency domain also lower, but the value, the matching it will give you is not that much good. So you can check both, and this is how you're gonna match and scale. So performance-based building code prescriptives, we have a specific, this specify fixed criteria and procedure that construction must adhere, and the engineers don't explicitly assess the structure real performance and restrict the use of advanced structural systems, and this leads engineers to assume. But for when you come to PBD, you are flexible. Like engineers will become like architects, you know, they have a chance. Address the limitation of prescriptive code by making seismic performance objectives, ensure greater building safety through detailed evaluation, allow exceptions to standard code requirement based on through the performance assessment, encourage the use of innovative and cost-effective building. So it enhances structural performance, improve cost, and it will achieve a lot of objectives. So this is the procedure of performance-based. First, you have to start from elastic analysis, then go to formulation of analysis of nonlinear modeling, then check the result and interpret the result. This is the. So this one we discussed already. So in the operational level, you expect less than 5% damage, okay? In the immediate occupancy level, you lose about 15. You expect like 15% damage. In the life safety loss, you expect about 30% of the damage. And in the collapse prevention, you expect almost, it will not collapse in the collapse prevention, but totally the structure is damaged greater than 30%, but you don't allow collapse. That is the idea of collapse prevention. So we have service level 50%, okay, probability of accident in 30 years, 43 return, and DB 10%, probability in 50 years, and MC level 2% of probability in 50 years. These are the performance objectives. You can go ahead and read, okay, and these are. But the collapse prevention, extensive structural damage repairs are required and may not be economical. But for code level, this DB level, moderate structural damage, extensive repair may be required. But for service level, structure to remain essentially elastic with minor damage to structure and non-structural element. These are the points. And this is what we discussed. This is MC level. And the 2/3, we're going to have DB level. And we have service level. And this is the damping ratio recommended, 5%, 5%, and 1.6%. This is the formula for return period. And this is also the same for evaluation purpose, service level, as we have seen now, and MC, and roof drift, 1.5 to 2.5. This is for damping, basically. This is also 2%. And these are the issues, and SLE level, DB, all this is what we have discussed. So you can go ahead and see the same information and the remark also here, the purpose why you do MC level, DB level, and service level. So service level evaluation, just use linear model as we have discussed, the response spectrum. You can use response spectrum and critical damping from 1.5 to 2.5. And load combination also the same, dead load, live load, reduced live load, 25%, and this is earthquake. When you take earthquake, 100% in the X and 30% as per the code. Once you take Y 100%, then you have to take 30%. Then R factor, omega factor, CD factors are all taken as unity. Acceptance criteria for DC 1.5, deformation controlled, and DC 0.5, force control. And the strength calculations use expected material. Okay, expected material 1.17 for rebar and 30%, 1.3 for concrete. Story drift will be 0.5%. And for MC level evaluation, use nonlinear model and nonlinear response history analysis. And 11 pair, as we have seen now, 11 pair is expected. It was 7, but now the code instruct 11. And generally 2.4 of the constant modal damping is used within the small fraction like relay damping and other. And average, as we have seen, you have to average the demand. So we have deformation control and force control. This is for hysteresis loop, okay? We have, this is as per the test, and we will use this back one curve, okay? This is the nonlinear modeling, we will use that. So as you can see here, force controlled, this one is deformation controlled, and this should be force controlled. The behavior is ductile for this one, and for this one, it is brittle. And we have critical and ordinary, we will see it, okay? Main consideration on which item to check for the performance, this one also we have discussed. All these global and local responses will be checked. Now, when we change our design from linear to nonlinear, for example, this is fiber modeling. If you are using fiber modeling, ETABS, it will give you, I mean, automatically it will, for example, this is the confined area. You know, shear wall, we have edges, and we have also here unconfined and confined. This is confined for shear wall, depending on the design. Then we have, for example, rebar fibers, as you can see here, and we will give a stress strain curve. And we have also for concrete, we're going to have concrete fibers. So this is a stress strain curve will be given, okay? So one thing I want to discuss here for confined and unconfined, okay? Confined and unconfined, this is the unconfined. If it is unconfined, you see the capacity is very low. But if you use full confined, it will go up to here. So confinement is very important. This is project team combination for the client, architect, structural, PVD specialist, and site specialist, and PVD peer review should be there. The other thing, MC level as ASCE 4170. This is transient drift at least 3%, okay? Not exceeding 3%. Residual drift also, we are not exceeding 4.5. Maximum mean value should not, and coupling beam also, as you can see, ASCE 41, column, ASCE 41, shear wall, it will give you this amount, you know. And you should be familiar with what does it mean 0.05, 0.02. These things, they are the stress levels, okay? Stress strain levels, and you should know that. So most of this ASCE 4117 is, we will see it now. It will give us everything about the rotation, moment rotation, the capacity. Once you have the section and you have the rebar, top rebar, and tensile rebar, this is for compression and tensile, and it will give you the capacity. So this one is also damage analysis. You can go ahead see, for example, primary, secondary for concrete and for shear wall. We have immediate occupancy, life safety, and collapse prevention, okay? And you can go ahead and it will give you. This is the damage, what we have seen. The different codes, they will give us this inter-story drift, okay? 1%, 2% for moderate, extensive, and complete. So this is the ASCE 4117 modeling. Once you know, okay, the bar, tensile bar, row for bottom, row for above, and row balanced, and if you know shear, BD, and FC, using this, okay, that's why we are doing in performance-based, why we are doing linear analysis, it will give you these values, okay? Once you know this value, ETABS will extract these values, and it will give you the plastic hinge angle and these modeling parameters and acceptance criteria, okay? But that's why in performance-based, why we did linear analysis, because to know the capacity as per this codes. Okay, we have conforming and non-conforming, and you can go ahead and read here what is conforming and non-conforming with the shear strengths. And we have this pushover dynamic and static procedure, nonlinear static procedure, nonlinear dynamic procedure. We can use V will be determined. Okay, once we know the V and all these sections, then directly you can go and you know the A, B, C values and immediate occupancy, life safety, collapse prevention. You directly come and take from here. So ETABS directly you will choose the ASCE 4170 modeling parameter. Once you choose for beam and column, and if you say take the rebar from the design, from linear design, then it will give you. So for you, no need to go to lab or and to know the capacity of your section. Okay, this is very important. So here we have 4 sections, as you can see: beam controlled shear, and beam controlled by inadequate development, and beam controlled by inadequate. You have to check all this. Most of the time, beam controlled by flexure we are using. Okay, so all this table is very important, and I will show you that also. This is the force deformation. As you can see, this is the A, this is A, and B, and C. Okay, the C values. This is the C. And immediate occupancy, life safety, and collapse prevention. So for you, once you know this, you assign this in your model. Then when the future earthquake comes, your building will capture the immediate occupancy, life safety, and collapse prevention. So when we say rotation, this was done in UCL. Okay, this is the report. So when we say 0.01 rotation, you see the structure is almost in good condition. And when we say rotation is 0.02, there is some cracks. When we say 0.05, almost, you see. And when we say 0.06, it is already damaged. The plastic hinge model passed already. So at least to know this, the rotation is good. I mean, it will show us. And this is hinge assignment. This is how we assign the hinges. Okay. And I will show you now. This is for fiber PM3. If you have shear wall, we have fiber. And this is for pushover case. And this is for pushover again. And this is load case pushover. This is for the beam M3 hinge. And this is, we will see it now. This is the force deformation, and this immediate occupancy, life safety, and immediate occupancy, and collapse prevention. It will take from, okay, ASCE 4170. And this is for the shear wall. So prescriptive code and versus performance-based design. Public, will the building be safe? Will the building collapse? All what we have seen, how much will be the repair cost and everything. Structural engineer, if you are using prescribed code, we don't know. The engineer will not answer these questions. But if we are using performance-based design, we know the capacity, we know the life safety stage, we know the collapse prevention, we know everything. So will the building safe? Will the building collapse? Can I use the building after a given earthquake? All these questions, then if engineer using PVD, then he can answer now. So by shifting our paradigm from prescriptive code-based design, performance-based design, we can answer. Okay, we can answer. So this is, we have seen it. And why start performance-based design with the client? For example, performance-based design begin with understanding the client objectives. For example, when a client asks, what is the benefit of applying PVD to my project? They will ask, why I'm using PVD? Our response should be, for example, the key performance-based design for the client achieves a high and clear defined performance level compared to conventional code-based design. provides variable and certified performance outcomes based on explicit engineering evaluation, and deliver documented performance objectives and offer formal performance certificate and so on. And client value proposition improves safety, reliability, and reduce uncertainty about damage and greater confidence also. This one we have seen it already, MC level, DB level, all this the same. And this one also occupation, immediate occupancy, life safety, and collapse prevention. So any repair or minor damage these partitions, and near collapse, this is very little damage. And as you can see, we are giving percentage. Yeah? This is CP99. For example, life safety may be 70%. This immediate occupancy, you will give 30 or 20. So performance level concepts, depending on the risk category 4, 3, 1, and 2, you are advised, okay, to use which level. You have to maybe earthquake density like service level, DB level, MC level, okay? For example, if your building is in 1 and 2, as you can see here, you are allowed until collapse prevention, okay? If it is 3, until life safety, okay? If it is 4, life safety. So depending on your structure also and the capacity, the intensity of the earthquake, you have to take it. And this one, as we have discussed, if you use linear analysis, this is the result you will get. And if you are using nonlinear analysis, this is the result. This directly give you different results. So linear analysis is not adequate. Then again, performance objectives, as you discussed, service level and MC level. And material, you have to use expected strengths. And model, this is linear model, this is nonlinear model. Damping, most of the time, 0.5, this is 5%, 5%. And the response spectrum, as we discussed, dead load, live load, reduced live load, and earthquake, 30%, X and Y. Nonlinear, no reduction, okay, only live load. But this one is 1, and you have to use 11 pair of ground motion. And linear or nonlinear analysis also the same. 3 pair of ground motion. By the way, linear analysis and nonlinear response time analysis all the same. Only the model is nonlinear. And load reduction factor. This is, as you can see, 1 here from 1.3 to 1.5, and FU is just 1. And response spectrum DCR, okay, 1.5, and this is DCR 1.5, and nonlinear DCR 1. Both here, it should be 1, DCR. Okay, demand capacity ratio should be 1, yeah, for both. But force controlled, they will reduce 0.7. So this is the initial information from architect, then code-based. Okay, once we do code-based, we do performance analysis. For performance analysis, service level and immediate occupancy, structural model analysis, modeling analysis, and evaluation. Does the performance meet selected objective? Yes. Then peer review. Okay. Then report. If it is no, again, we have to go to code-based. Because all these things for soil report, plus seismic hazard assessment, with tunnel test, all required in the code-based. And this one is also, it will give you the drift amount in the immediate occupancy, in the life safety 2%, in the collapse prevention 3%. Okay, and everything you can go ahead and see. Now, general concept, a minimal level of safety for all buildings at MC level, and alternate design with predictable safe performance, and high limit of selecting seismic force resisting systems. But here, no limit, as we discussed, performance based to give us the option. And these are also load combinations, okay, so for serviceability, limit state, and earthquake, and quasi-permanent also, and imperfection loads will be also added. And this one also, as you can see, they load, live load, and earthquake. And brittle, if it is brittle, 1.3 to 1.5 times, and ductile, the mean demand. And capacity, you see reduction factor, this code will take from 0.65 until 0.9, but here we don't use. And material property, as we said, concrete strengths and steel strengths. And for the performance, as we said, expected strength 1.3, 1.17. So DC ratio 1, as we discussed. And from here also, you can see 1.17 for steel and 1.3 for concrete. This is expected material also. And the stiffness modification, as we have seen, the stiffness modification is very important. So for service level and for MC level, they will give you for flexure control and shear control, there is different recommendations, okay? The most important concept in performance-based design is capacity design concept, okay? We have load and we have moment, as you can see, moment and shear. And these things are brittle, and the middle one is ductile link. So don't yield. So to ensure ductile failure, we must ensure that the ductile link yield before and the brittle link. So the shear capacity should be higher than the moment. And this is the idea of performance based, because if you make all your building ductile, the computational power will take a lot of time. So you have to select which element, like coupling beam and shear wall areas and in the beam. Some places you have to select and make plastic hinge there, okay? Otherwise, if you make all your building nonlinear, it will take too much time, because nonlinear take too much time. So this is the capacity design concept. And this one we simply bring for you to see for concrete and steel, the force information and the strain capacities. And you can see it. The other thing, component classification, as we discuss now, we have deformation control and we have force control. And in the force control, we have critical action and ordinary action. This one already in the code is included. You don't need to memorize. I bring it here for your information. So deformation control means it undergo nonlinear behavior, yes? But force control means not expected to undergo nonlinear behavior. And for critical action means, this is the most important, the force control action, the failure of which is likely to lead to the partial or total structural collapse. This is critical action. But for ordinary action, it is not, okay? It will not lead to the whole collapse. And this is the B value. There is a value, B value. And what, this is the experiment, by the way. Test on slender walls was made, ACI. And the shear shows that shear strength decrease with increasing in elastic flexure. As you can see, when the inelastic flexure increase, the shear strength is also decrease. This is the first thing. The other thing, what they see is based on the experiment, okay? VNE means based on the experiment, the shear force based on the experiment over based on the ACI formulation around this area, they found 1.5, okay? So they bring this value here. So B value 0.5 VNC over V, this CM, okay? VNEM, it will give 1.5. Okay, this will use it for capacity determination. And this is for force controlled also, just to show you the critical combinations. Like you can go ahead and see what is this total force. This is for non-seismic portion of total force. B is the factor, as we have seen now. Rn is the nominal strength using the applicable material, and this is the resistance factor. All this is given, okay? Now the idea is what I want to show you. This is Equation 5a, for example, this is for nominal strengths and this is for expected strengths. This is the capacity. This is also non-sensitive to vertical actions. This is critical action, sensitive to vertical action. When it is like transfer girder and outriggers, we will use these combinations, okay? The same thing, but for nominal and strengths. And ordinary, but don't, this will be given in the code. You don't need to memorize all these combinations, okay? But the one thing I want to show you, this is non-sensitive for vertical actions when the critical action, okay, for force controlled. For example, if it is non-sensitive to vertical actions, what we can do, come here, QNS, okay, this is QNS, yeah? So what we can do, this value, if it is for vertical action, if it is 0, then QNS plus 1.3 I, Q total QNS, yeah? So this QNS value can be 0. Then if it is 0, 1.3 I total will be, you see, QNS will be 0, then 1.3 total less than this value. So this is just for your information, but as I told you, no need to. You see, everything is given here, critical, ordinary. The only thing you have to choose is which structure you have. For example, if it is coral, then the phi and the b factor is already given. So for you, no need to calculate. Only in the code, everything is given. So you can multiply it here, you can get the capacity. Okay. Again, here we have, this is for MC deformation controlled actions. We have acceptance limits, okay? Different regions in the shear roll, the code give us what will be the acceptance limits, okay? You can use those. This DC ratio should be 0. This is for the tension side, this is for the compression side. This is also, we should know, no confinement. If it is no confinement, just if you check here, no confinement 0.01. If it is full confinement, you see the capacity 0.05. Okay, from 0.01 to 0.05. So the confinement effect is even for full confinement, you see 0.05. So detailing of confinement is very important in the PBD. So this is service level. We have service level here. Story drift is 5%. So as you can see here, effective linear response, laser and MC level, mean transient story, 0.05 or maximum 0.045, residual 0.01 or 0.05. So this is MC level. Now application of PVD, you can see for San Francisco, and this is also Philippines. Almost in the US, everything is performance-based design. So before we go now, this is the result in Perform 3D, and this is in ETABS. And this is what I want to show you in the lab. Okay, seismic rotifico rectangular bridge pier. What they do, lateral displacement. We have lateral displacement and base shear. Yeah. So we have the gravity load and we have horizontal. So they will apply loading and unloading, and they will make loading and unloading. Then we get hysteresis loop. Once we get this hysteresis loop, we will get the back one. And the rule also required for loading and unloading, because this is the energy under this backbone. It will tell us the amount of energy, cracking, yielding, crashing, all these things. So this is just for your to remind you. So as you can see, this is the initial yield point. This is first yield point. This is the strain hardening area. This is ultimate strength. This is ductile limit, strength loss, and residual. This is the force deformation behavior. And this one also, immediate occupancy. And we have life safety and collapse prevention. As you can see, life safety is around 75% of the collapse prevention. This is as per ASCE 41. wide range of, as we have seen now, ASCE 41 almost give us everything. Okay. This is the ASCE 41 again. Once we have the rebar and the section and the shear and the B and the D values, then we can have everything we need. Okay. So the concrete is this one. As I said, confined and unconfined. When it is confined, it go beyond, you see. But if it is unconfined, we go like this. This is for steel. We have upper yield and lower yield. So this is the 0.1% yield. And we have the strain hardening, tensile strengths, and so on. So this is the, we have different kind of hysteresis loop, from difficult one, okay, complicated, most complicated one. And we have also EPP, we have reinforcement steel, for example, this one, and exaggerated pinching and concrete models, okay. Then this is the idealized nonlinear modeling, okay, idealized nonlinear modeling. As we discussed, we have fibers for fiber hinge modelings, and for component level is very easy, force deformation curve, we will see it now. And if you have shear wall, you have to give, for example, this is the beam, and if you, this is the shear wall, for example, this is column. If you want to use fiber hinge modeling for the column, it should be divided in this very small, like this, and you have to give stress strain curve for each one. So imagine you are designing a 100-story building, and how many columns you have, how many shear walls you have. So if you are giving a stress strain curve, and for each, it will be very, very difficult. That's why you have to select where you have to make ductile, and it's better. This is, you see, this is what I told you. But in Perform 3D, you have to give component types, okay? Component types. Geometric nonlinearity, as we know, linear, we have geometric nonlinearity and material nonlinearity. So depending on your structure, whether you need delta or first order or second order, it depends on your MC level, you can see. This is the geometric nonlinearity, P delta, big delta, and small delta. This is the imperfection I told you. Okay, the imperfection load, it should be captured as a notional load. Okay, notional load, and P delta is for the component level. But big P delta is. So this is analysis. We have the target response spectrum, and as you can see, target response spectrum depending on the location. Once you know your target response spectrum, then you have to match it. This is a seismo match, and you have to bring all the earthquakes, 11 earthquakes, and you have to define your response spectrum, and you have to do matching. After matching, it will give you target response spectrum like this, and all the others, for example, before matching and after matching also, it will give you. For example, this one, you see, this is target response spectrum, the red one. And this is mean matched. Once after you match it, the 11 earthquakes will be matched and it will come. So from 0.5 T1 to 2T, the fundamental period, it should not go down. And this is what it shows. You see ground motions, and after matching, this one before matching. After matching, you see they are concentrated here. This is the same thing before matching. This is also the same thing. Okay. This is for different damping. You can choose different damping and you can match it. And this is also the same. This MC level, 2/3 will be dB level. So you have 11 ground motions. You're going to match it and you're going to apply it in your building. Okay. this is the complexity of from linear to nonlinear analysis. This is very complex. Okay, so uniform hazard and conditional mean hazard. So uniform hazard has the same probability of accidents all period from this, and the spectral shape of UHS may not the real ground motion is conservative. Okay, only this set of UHS spectra, but conditional mean will match the ordinate of the HA only at the intersection period, can yield more realistic. So from the, if you want to conditional mean the spectrum is more realistic than the uniform hazard spectrum. That's what we want to show you here. Then service level is 1.5% and MC level is 2.5%. So let me go to here. Okay. So this is not linear. So what we did was we were here, yeah? We were in the linear analysis. Now we are satisfied. We know the section, we know the rebar, and we go to display and we see story plots, and we can see, for example, for a response spectrum, or wait, this one. Okay, let's choose one. Okay, we want to see the response, okay? We want to see the response. This is 0 because we have to choose time. Time, for example, let's make it maximum. If at the maximum time, because it will start from 0 and it will go. So it will give you the maximum story displacement. As you can see, if you want, you can take it from here. And you can get all the information from displacement, drift, displacement, maximum story, drift, story shear, overturning moment, for example, overturning moment, and shear force, and stiffness. Okay, stiffness, it's working on it, I think. And shear force. This is the shear force. So you can get whatever information you need from here. Once you do that, you will change this into nonlinear model. How you gonna do? Now it is already logged, yeah? What we did was we just select, okay, and of the property frame section, you're gonna choose all the sections, okay? Then you're gonna assign frame, and now it is locked because hinges, okay? Once you say hinges, it will give you the option, okay? It will give you the option and you're gonna apply. But what I want to show you now, let's see the result. For example, let's go to here, and the time is here. And what we want to see, for example, BCD apply. This is already 50, in the 50th second. As you can see, we have 5,000 steps, okay? 5,000 steps and 6,382 steps. Already at the 5,000 steps, your structure is acting like this, still not past the collapse prevention, okay? And let's see if we have 60 seconds, because it depends on the earthquake length, the duration of the earthquake. So you see, at 60 also like this. And you can go ahead, for example, pushover. Pushover, for example, in the Y direction, we have 10 steps. Let's start from 1 for pushover. Apply. This is for pushover, for example. This is in the step 1. Now in the step 2, you see some hinges are already created in the step 2 and the step 3 and step 4. Again, step 5 and step 6 and step 7. it will go like that. You see, still not fail. We are in the BC direction, range 9 and 10. Okay, so this is for push X. If you go to push Y, we have 3. So let's go to here. In the X direction, push 1. This is push 2. And this is step 3. You see, at step 3 already we have it. So every earthquake, for example, let's go to Lome Parita. And let's choose, if it is 0, in the 0 second, there will not be nothing. But let's say at the 10 second, apply. Now in the 10 second of the earthquake, you see, almost the hinges are formulated. Let's say at 20 second. 20 second already like this. 30 second more hinges. So performance evaluation means like this. You take linear analysis and you are checking now for this amount of earthquake, how your building is behaving, you know. If some of the hinges are red, that means you have to change the cross section or you have to change something. So let's see this one, the same area. Okay, so in this way, you can see again for the moment, for example, if you want to see the moment and everything, let's see, for example, moment, apply. But now it is 0, yeah, because we are here in the 0. Can you make it max? In the maximum, for example, the maximum moment. Okay, you see? But let's go to, for example, date. What this one is telling you is that when the earthquake for earthquake lateral forces, the moment diagram you see, yeah, they will resist it in this direction, yeah. For the dead load, it will show you the moment diagram is like this. I think option display. White background. Okay. Okay. So the other thing, because this is nonlinear times tree analysis. So what we are going to do, if you want to capture the video, you can go here and multiple step, because this is like 30 second, 40 second, 50 second earthquake. So depending on the time, let me show you. Depending on the time, it will give you, for example, this one. It will, for at 0, it is 0, yes? There is no nothing. But if you are in the 10 second, you're gonna apply and you will see shear rod. So moment. So what you can do, you can take video from here, capture video, and it will give you the video. Okay, this is what you can do, and you can get a lot of information from here. If you need report, you can go here and, for example, create report, show project report. Okay, now it is generating a report. Okay, until it's generating the report, let's go to our slide and Okay, now I think you have some idea. So now structural evaluation, local and global response, as we discussed. The same thing, you can take it into performance based. Now I cannot, in this laptop, I don't have perform, but this is our building, G+5, okay? Once you take it, you will check the first is translation, second is translation, third is rotation. And again, you can check for different earthquakes, okay? Different earthquakes, it will give you, for example, immediate occupancy level or life safety level in the component. This is component, you see, in the component. If you need entire, you can get in the entire. So from elastic to non-elastic, you can see the performance. And this is a combined report. It will give you all the displacement, drift, shear, overturning, okay? I will show you that one. This is in the perform 3D. It will give you also moment, okay? Moment in shear diagram, as you can see. And you can select a line or point element or section. Maybe in the next webinar, the fourth one, we will do perform 3D results, okay? And this one also in the perform 3D, you have the option of demand and capacity. So this will be accepted values, and this will be non-accepted values, okay? Demand capacity curve for FEMA 440 idealization. Once you give the point, and once you define the spectra, and for this case, we give 0.5 G, okay? And when we check, this is the performance point in the PVD. The most important tools in Perform 3D, this is DC ratio and this envelope. These two will give you the overall, okay? Because this is, for example, 100, it will give you the DC ratio, okay? For example, we have here one, for example, let me show you 1, 2, 3. If you click here, it will give you the performance, okay? And this one also will give you the performance. So all of the performance should not pass 1. If it is past 1, then immediate occupancy, most of the time it will pass. But for life safety, you see 1, this is DC ratio is 1. And you see 1, 2, 3. This is for column, beam, column, and shear wall. All of them are under 1. And you have the choice also, maximum, mean, maximum, and you can choose this, and you can see the performance. So Perform 3D will give you a better performance check, because all of your should be under here. And it will give you also energy balance. How much of the energy is dissipated by which component? This is also, you get this information from there. So this one, evaluation of local responses, as we said, most of the time we use ASCE 41, ASCE 318, 18, ASCE 41. And as I told you, maximum you have 11. So once you get the moment, you have to divide by 11 and you will get the force. Deformation also, once you get different deformations, you have to take over 11. So this will be because you are taking 11 earthquakes, yeah? So we have to take the average for evaluation purpose. So sample result, this is some of the researchers I took, for example, for shear wall, okay? For shear wall, for example, this is a strain limit, okay? This is the strain limit, okay? This is for crushing, for concrete, and this is for yield. So if it pass your limit, what you can do is increase vertical reinforcement, okay? For concrete, increase confinement, then it will be in the limit. So this is how for easily you can see, okay? And this is for boundaries, and we discuss also confined and unconfined cases. And the strain prediction, as you can see, strain, this side is big because this is in the tension, this is in the compression side. And this one, as you can see, also we have capacity. This is capacity. This is limit. Okay, 1.5, because in the we will multiply the average. The average is 1.5. Okay, 1.5 average. This is the black one. Now This one, as you can see, it is already in the limit, yeah, in the capacity. So what they did was only changing the spacing from 0.5 to 10. The capacity already, you see, out. So you are in the limit. So when you do performance-based, you can get this kind of information. And this is in the column. Most of the time, there is no much. This is the, you see, this is one, the limit. But most of your are very small because DC ratio theta is very small, yeah, compared to the slab. This is for column shear. Okay, column shear also. For example, only 2 points are out, yeah, from the limit. So what you can do after revision, revision? You can change, for example, from 30, okay, center to center 30, you can change it to 25. Then all this will be inside the limit. So this is before revision, this is after revision. This is demand capacity. For the coupling beam, we have conventional and we have diagonal. As you can see, coupling beams are very sensitive for earthquake. So what we can do for that also, for example, you see we have L here. From here to here is L. This is theta. So we have here. So once we divide this one 0.04, yeah, 0.04 to the maximum 0.08. So we have 1 here, but our result is 0.08. So it is also in the limit, rotational limit, okay? So this is the idea of performance-based design. Once you do it, you can see clearly what is the idea. And this is also energy dissipation, okay? The energy dissipation in Perform 3D, it will give you which amount is, dissipated by column shear or shear wall. And this is for dynamics of structures. You can go ahead and check, okay? So different kind of kinetic energy, strain energy, modal damping, alpha M, beta M, energy fluid, and inelastic energy. So this is, you can see easily. So in general, the advantage and disadvantage of performance-based seismic design, the advantage, okay? The advantage, more reliable achievement of the intended seismic performance and suitable for complex buildings, for example, irregular structure, multiple tower on single podiums, allow flexible beyond some prescriptive code requirements, accommodate challenging architectural features, enable the use of innovative structural system and material. But the disadvantage, high computational effort. As you can see, extracting ground motion, changing into moment from linear to non-linear in the application of plastic hinge modeling, fiber hinge modeling. And even in Perform 3D, you are responsible to fill all these things. But ETABS, at least it will give you, and you have to check it, the hysteresis loops and other things, okay? So it's high computational and complex analysis procedure, require preliminary design. As we can see, first you have to do linear analysis, then from linear analysis, you have to go to non-linear analysis. So often start from code-based design, yes? So time-consuming analysis and design process requires significant computational resource and data processing. That is it. So lastly, I want to say this is Dr. Grams H. Paul. The Perform 3D was invented by him. So what he says, estimating the inelastic property for a real component is not a simple task. So it may be tempting to argue that since the inelastic property are so uncertain, because to know the inelastic property is not easy. There is little point in using inelastic analysis and elastic analysis to be sufficient if someone can argue like this. But if there is substantial inelastic behavior in an actual structure, the result of an elastic analysis may be of uncertain value of making decision making, because as we have seen in that, if you make a linear analysis, the result here, if it is non-linear here. So as a tool for obtaining information for design, even a crude inelastic model can be more useful than elastic analysis. So please keep in mind that the goal is to get useful information for design, not to calculate exact responses, okay? So that is this is some of the published books, papers. You can go ahead and read. But let's go back to our report. So we say report, as you can see now, ETABS will give you everything. ETABS will give you structural data, property, assignment, load, function, analysis, result, as you can see here. It is almost 5,000 pages are already generated for you because our analysis is nonlinear, okay? Let's close it. And so we see you can display, as we have seen, everything. And let's see, for example, we can see cumulative energy, as you can see here. For different, you can see for pushover, for example, nonlinear time history analysis. For pushover, you see potential, but for nonlinear, yeah, global damping is included, and potential is very small, you see, because this is nonlinear dynamic. If you make it potential pushover, almost this is this is potential energy static is huge, you know. Nonlinear hysteresis damping also we have, but when you change it into nonlinear, global damping is taking much amount of energy. So you can find qualitative amount of information about the energy dissipation of different earthquakes. You see, the whole amount is already global damping. So this is the energy, and the other thing which you can get, cumulative energy component, storage response plots, response spectrum curves, plot functions, hinge results. Even hinge result, you can go ahead and check each hinge result. It will give you, okay, from which pass or not you can see, you see. Okay, for example, this one is ground floor frame and column level, and this is C1H7 auto. Okay, this is the auto. Basically, we give auto, yeah. Rotation distance, we give 0.1. And as you can see, this is the hinge result, and you can change. For example, we have two hinges, yeah? So the other hinge also, you see, in the other direction, it will go like that. And let's go to C2, for example. And we have two hinges. This is the one hinge and the other hinge, you see, in the positive X. So you can go ahead and check like this. And depending on the hinge you give, you can find the hinge results. That's what we want to show you. And the other thing, okay. The other thing what I want to show you, the design part, the analysis part, no. Display, and you can go to show table. And you can see everything in tabular form. Analysis form, joint results, structural outputs, okay, base reactions, everything is here. That is what I want to tell you. So I hope from my side, I'm done. If you have any questions, you can ask. Thank you so much.
Thank you so much, Dr. Abate.
Okay.
That was very informative and very descriptive. You actually went into a lot of detail, and I'm sure the attendees do appreciate all the information you have given them. So thank you for attending this and enlightening all of us, myself included, although I'm not an engineer. So thank you for that. And we do have a few questions. Maybe you can address them and then I can just read them out to you if that's what you'd like. Because they're under the Q&A function. I don't know if you've got the view for that. But the first question is, can you please share the name for time history software scaling?
Okay, thank you so much. For time history analysis, I think he's saying the data, yeah? Here, Europe's websites or USGS, and there are also other international websites. You can go there and you can extract the ground motion.
Thank you for that, sir. And then the next question from Tulasi is, what is the main difference between the ASCE and Indian code on the dynamic analysis?
This code-based design, we have a lot of codes, for example, ACI, India, Eurocode, Egyptian, and so on, India. So principally, I don't think there is too much difference. Okay, I don't think too much difference because performance-based is unique. I mean, as per your local condition, you can tailor it as per your requirement. So there might be some changes. I mean, I don't know Indian codes really, but there might be some changes. But performance-based is universal, you know. That is the idea. And there is one guy, he says, can you please share the name of the time history software, scaling software? He says like that, yeah? I see there.
Yeah, that was the first one. And then
the first one.
Yes, sir.
Softwares. This one is Sesamo Match. Sesamo Match. This is, you can go to Sesamo Match, and if you have organizational email, they can give you until 4 seconds. They will give you student version. So you can go there and register. Sesamo Match. The software is Sesamo Match.
Thank you, sir. And then the next question, also from Tulasi, and they're asking, while doing, oh no, sorry, that's further down. I just want to go in chronological order. And okay, so the next question is, what is the limitation between the use of ETABS and RCDC?
ETABS is very well-known software, and it is very flexible, especially for linear and nonlinear analysis. And as you can see, you can do linear analysis, nonlinear. In the nonlinear analysis, plastic hinge modeling or fiber hinge modeling, it will give you, as per the ASCE 4117 table, directly it will give you the capacity of your beam and everything. And to be frank with you, I never use the other software. Mostly I use ETABS, SAFE, Perform 3D, and the other software like SAFE, ETABS, SAP. These kind of softwares I use. But SRLC, I think for post station, like RAM concept, I used it, but I never used it for Perform 3D. So RAM structure and this RSDC they are also famous now with time, especially for post station design and others. But I don't think there will be much. All softwares are the same. Most softwares they have the same capability and the same code. That is what I can say about this.
Thank you, sir. So also from Tulasi, he's got another question. And the question is, while doing the dynamic analysis, what happens if we define the factor of safety other than the code book?
Factor of safety. Because in dynamic analysis, as we discuss now, we are going to give the exact force deformation, the capacity, the stress strain into your structure. So we cannot give factor for when you do performance-based analysis, you have to use the real capacity of your structure. Okay, no need to use R factor, CD factor, omega factor, because we are assuming our structure is capturing our real capacity. So we have immediate occupancy, life safety, and collapse prevention. So if you give factor, you will not get the real MC and service level performance of your building. So that's why in performance-based in dynamic analysis, as much as possible, you have to use the real structure. No need to give factor. That is what we do in performance-based design.
Thank you, sir. And then the following question from Harry, asking will the video be recorded? Yes, it will be recorded. And in a few days, if you go into our YouTube page, it will be there as well. And it'll also be sent to you. Both the recording and the slides will be sent to your email. So the slides, it's going to be within 2 business days, and the certificate of attendance will be within 4 days. So just look out in your emails. If it's not in your emails, kindly check your junk mail, spam mail, or alternatively, if it's not in any of those, it should be in your promotions folder. And then we have a question from Temas again, and they're asking, the question I have is performance-based design and code design. What is the advantages and disadvantages on design?
Okay, the advantage and disadvantage at the end, we discuss this one in the conclusion. In general, the advantage of performance-based design is it will give you the chance, it will give you the opportunity to assess and check the performance of your building, okay, whether it is in the immediate occupancy, life safety, and collapse prevention. So the code based is like a prescriptive nature. If the code says you have to use 0. For example, R factor is 8, you have to use 8. That's all. In performance based, you are free. Engineers are become like architects now because we are free to check the performance objectives. To check, for example, we are not limited into different kind of structure of the code. Now we are free. So performance based is not bounded by code, but code is you have to comply. That's all. But in performance based, before the earthquake comes, you can extract 11 real earthquake, and you have to apply in your building, and you know how your building will perform for the future earthquake. So performance based is now very famous in our world, and it will give a huge amount of useful information about our building. And that is the difference between code-based and performance-based.
Thank you, sir. I'm just trying to go through the chat because there was something that I had informed them that we'd address closer, and that was from Given Toma. Given, if you're still around, could you please just put something in the chat box so we can answer your questions? Alternatively, you can reach out to us. We've got our information right here on the screen for our different entities, with EIT being the sister company which is overseeing both ECT and ECST. And then someone asked, yes, so how are we going to start that since we don't have financial stable? I'm not entirely sure what he's asking there. And then Sfiso was asking, can these designs be communicated to cross-professional industries like the interior designers or IT that want to use them for their writing connections?
I don't quite get it, but this
I'll
time,
just I also don't really get it, but I'll type it. I'll put it back in the chat box. Maybe you can just check it out. The question again. Okay, you see it. I just posted it now.
question and answer, yeah?
No, not in the question and answer in the chat. Yes, sir.
Okay, okay, let me see. Okay. Can this design be communicated to cross-professional industry like the interior designer or IT that wants to use them for writing corrections? Basically, everything can transferable, okay? We can transfer from one software to another software. Everything is transferable. If the IT guy, I don't know, IT, if they need it, I mean, for what? I don't know. I mean, this is a structural design, so maybe IT guy, I don't know how he wants it, but interior designers, of course, because as structural engineers, we will follow the architectural design. If we change any structure in the building, it will be communicated with the architect first, because we cannot change without the architect. If the revision, the architectural revision is done, automatically it will be distributed to interior designers, sanitary, electrical, mechanical, all should be notified. Okay, because being a structural engineer is not enough. You have to be project engineer also. The management you have to know. So all this information will be transmitted throughout the professionals. That's how we are doing. So that's BIM technology now in the building. We use BIM, and all the professionals will be distributed and get all the information. I think that is the answer.
Thank you so much. That brings us to the end of our presentation. Thank you all to those of you that attended and stayed till the end. We appreciate your time. And once again, thank you to you, Dr. Abate. We
Thank you
appreciate
so
you
much.
and the time you've given us. Thank you all and have a great day, or what's left of it, depending on where you are. Thank you. Bye.
Oh, thank you so much. I really appreciate it.